Welcome to Module 2, where we explore the mathematical foundations essential for understanding and building machine learning models. This module covers key areas: linear algebra, calculus, and probability and statistics, each crucial for enabling algorithms to learn from data. By mastering these topics, you'll gain the ability to interpret data structures, optimize models, and evaluate results rigorously in machine learning applications. Core Mathematical Topics Overview. Linear algebra focuses on vectors, matrices, their operations, and eigenvalues and eigenvectors, helping represent and transform data efficiently. Calculus covers derivatives, integrals, partial derivatives, and gradients vital for understanding changes and optimizations in models. Probability and statistics includes probability distributions, Bayes' theorem, and hypothesis testing to manage uncertainty and derive insights from data. Fundamentals of linear algebra. Vectors. Vectors represent ordered lists of numbers describing points or directions in space. They are fundamental for representing data features and inputs in machine learning models. Matrices. Matrices are rectangular arrays of numbers used to organize data or represent transformations. Key operations include addition, scalar multiplication, and matrix multiplication. These operations enable complex data manipulations. Operations: addition of vectors and matrices, scalar multiplication to scale vectors, matrix multiplication for combining transformations, eigenvalues and eigenvectors, unveiling data structures. Eigenvector: a non-zero vector that, when a transformation is applied, changes only in magnitude, not in direction. Eigenvalue: the scalar factor by which the eigenvector is stretched or compressed under a transformation. Application in PCA. Principal component analysis uses eigenvectors and eigenvalues to reduce data dimensionality by identifying the most significant directions of variance. Key calculus concepts for machine learning. Derivative measures the instantaneous rate of change of a function, essential for understanding how model outputs respond to input variations. Integral represents the accumulation of quantities, used in probability theory and loss function calculations in machine learning. Partial derivatives and gradients in optimization. Partial derivative: derivative with respect to one variable while keeping others constant, used to analyze multivariable functions. Gradient vector: a vector of all partial derivatives indicating the direction of steepest increase of a function. Gradient descent: an optimization algorithm that uses gradients to iteratively minimize the loss function in machine learning. Probability distributions, foundations for uncertainty. Normal distribution: symmetrical bell-shaped curve defined by mean and standard deviation, widely used to model natural phenomena and noise. Bernoulli distribution describes a binary outcome, success and failure, with a single parameter representing success probability, critical for classification tasks. Bayes' theorem, updating beliefs with evidence. Prior probability: the initial belief about an event before observing new data. Likelihood: the probability of observing the evidence given the hypothesis. Posterior probability: the updated probability of the hypothesis after considering the evidence. Statistical significance and hypothesis testing. Hypothesis: formulating a testable statement about data distributions or model performance. Statistical significance: determines whether observed effects are likely due to chance or represent true underlying relationships. P-value: quantifies the probability of observing data at least as extreme as the sample, assuming the null hypothesis is true. Mathematics as the cornerstone of machine learning. Theory: mathematics provides formal frameworks for algorithms and model justifications. Implementation: mathematical operations translate to code implementations within ML models. Optimization: calculus and linear algebra drive the refinement of model parameters for improved accuracy. Inference: probability and statistics enable prediction and uncertainty quantification. Key takeaways and next steps. Master key concepts. Deepen your understanding of linear algebra, calculus, and probability to build solid machine learning foundations. Apply mathematics. Practice applying these concepts in coding exercises and algorithm development. Explore advanced topics. Continue studying optimization, statistics, and matrix factorizations for advanced ML techniques. Integrate learning. Combine mathematical knowledge with practical model building to solve real-world problems. Thanks a lot for sticking with us through this module. We're just getting started, there's plenty more to explore in the upcoming sessions. So make sure to subscribe, like, and share to keep learning more about the fascinating world of machine learning. And don't forget to keep practicing these core concepts, they're the building blocks for solving real-world machine learning problems with confidence.